So in this question, we really have a difference in difference type setting, right? When we have a control group, a treated group, 2 time periods, and we're trying to figure stuff out. And there's also an extra bonus that the treatment is random, okay? That's a bonus, and that's a big bonus too. So we were able to measure student performance both before and after the introduction of the program, write down the equation that will allow us to estimate whether this program is improving student performance, specify what parameter captures such potential improvement. You should immediately think difference in difference. 2 periods, 1 treatment, treatment is random. You should think difference in difference. Even without reading the actual question, you should be able to write things like y is equal to beta 0 plus beta 1 times post plus beta 2 times time plus beta 3 times time times post. And that should give you a difference in difference estimator. But of course, if I was in an exam, I would try and kind of be a little bit more specific, tailor those answers to the question, right? So what is y in this case? Well, in this case, it's performance on the exam, right? What is post in this case? Well, it's a dummy variable for after you got a treatment, right? Or whether you got a treatment or not, right? Or post is the actual treatment, if the individual was treated or not, right? What is the parameter of interest? Is this intersection of time and post. Okay. That's what that is. Yeah, when post is just treatment, right? With post, I really mean treatment there, right? So maybe I should just say treatment. Treated. Treat. Unfortunately, our data consists of 2 repeated cross-section instead of being a panel data. So repeated cross-section means that I don't necessarily have the same students, okay? Could be a completely different set of students, okay? So I could be looking at students that are completely different. Does this threaten our internal validity? Causality of our estimate, or the parallel trend? The thing that rescues us is the fact that we believe that, or we are told that this treatment is entirely random. Okay? So if this treatment is entirely random, we certainly don't mind that we have 2 repeated cross-section on the 2. Okay? In fact, imagine that we'd only been able to measure performance after the introduction of the program. So we have the treated group and the non-treated group. Would it be possible to study the effects of the program? If so, how? We could simply do a difference in means. We could do a mean comparison of the people that were treated and people that were not treated. So this particular bit here would simply be performance, y, beta 0 plus beta 1 times treatment. Treat plus epsilon. And if it was indeed random, this beta 1 should capture the causal effect. Okay, so note that if you can answer a question like D, it becomes obvious that of course we don't care the fact that we have repeated cross-section. Actually, we didn't even need the first bit, right? The first bit was irrelevant, and it was irrelevant because this treatment was entirely random. Okay, had no, had no special effect on one or the other. How about C? Well, C is again another one of those things that are trying to confuse you because, sure, parental income might differ from individual to individual, but the expectation on the treated group and on the control group is that they're the same. So, sure, they will be different, but in expectations they will be the same. Why? Because of the random nature of okay. And of course there's a stupid question, well, not stupid question, but a question that should really hit you in the head that it's wrong, right? Like stupid in the sense that stupidly easy question, right? You should know that answer almost immediately. Imagine that we only been able to measure performance before the introduction of the program. Would you be possible to study the effects of the program? Of course not, right? How could you, right? So if that comes up on an exam, right, you will know how to do that. If you don't know how to do that, you should leave it empty, right? Right. Okay. Okay, and that's pretty much that question. So really this question 10 boils down to difference in difference estimator, part A. If the treatment is random, what can be said about comparing means, for example, right? Mean comparison, and mean comparison seems to be a good one to look at, and the likes. Okay. So far, so good. Yeah. Now, let me tie this up a little bit. This mean comparison with the question on workers and new machines. Okay. We had a question that you could check out the previous video, but the main idea is this: that you had some kind of workers here and productivity. New machines were introduced. Actually, it reduced productivity, but the progression was with the same slope. So these machines actually tended to, not do very well. Now, the problem with this is that we don't have a treatment and a control group. Okay, we don't have a treatment and a control group because everyone is getting the treatment, right? All the employees are getting the treatment. So in this case, even though, for example, performance might have been improving over time, difference in difference estimator will take care of that because in this world we always have a treatment and a control, right? If, for example, imagine that some individuals were not treated, so they were sticking with the old machines, and you got data like this, and these were the individuals that were sticking with the new machines, and you got data like this, then a simple difference in means would have worked perfectly fine, right? A difference in means would have worked perfectly fine. So hopefully, when you look at this question, you can tie it in together with the idea that why did a mean comparison not work very well in that new machine bit, but why does a mean comparison work very well in this particular bit here?